Thanks, everyone. Thanks to the panel. So no small task to summarize this whole thing and send us off into the evening feeling great about ourselves and looking to the future. But I'll take a little stab at it, and it'll be 10 minutes, and we'll be out the door in no time. Okay, it's going to be lighthearted. You can see here our man with the VR is pointing to the clouds in anticipation of the future. Okay, so the case for timber, the case for innovation. We used to design like this, right? So a manual process, hand-drawn, lots of labor, slow, but still an art to it. You know, drawings and design look like this, right? It's hand-drawn, very simple lines. Please don't make any changes. This took all day. This took all week. This was the process. This is how buildings were designed. This is how the drawings were produced. This is how we used to do computing. Not me personally, but maybe some of you in the room. But anyway, so it used to be, you know, large scale. This is mainframe computers, computational time, you know, over an entire weekend to do what we can do today, you know, in our pocket over a few seconds. This is how we used to do testing. So how many EORs can you hang from a panel? Right? So manual processes, try it out. Standards were less back then, but, you know, it still worked. And this is, you know, far back in the day how some of our buildings looked, right? Very simple, easy to construct. The forms were not exaggerated, not very complex. So what does design look like today? Well, this is how we can design now. This is how we can do automation and calculation. This is the full parametrification of design. Now we can take those rote manual tasks of calculations, the 20 drafters in a room, and it can all be done in a few clicks, right? This is the dream of consequence-free trial and error. This is how we can produce buildings now in terms of the drawing production, in terms of what are the documents a builder needs, what is the content a builder needs to install a building, to construct the structure, right? It's a full 3D model. We've seen this all throughout the day. Full 3D model, interactive. You can do sequencing, time-lapse. Every screw is in there. Every hole is in there. It's all contained in there. It's the full kit needed to know how this building will come to life. This is what we're doing on quality control of the materials that are going into the building. This is Kolesnikov at their plant out in the Kootenays using laser scanning on all of their boards. There's an AI machine, an imaging machine here that detects knots based on the thousands of board feet that it's received in the past and can then automatically detect knots for the board that it sees now right in front of it. And it can optimize that board to produce maximum yield. So incredible technology. This is how we can fabricate now. This is a spearhead just down the road from Kolesnikov out in the Kootenays. I could watch this forever because it's mesmerizing. But this is, you can create these forms, you can cut these shapes that previously were, you know, very difficult. Not impossible, but very difficult, right? So this is the technology that we have now that enables us to do forms that we couldn't do in the past. This is what testing can look like now, right? Instead of hanging from something, now you've got a hydraulic actuator, fully instrumented out, collecting every last piece of data, every last piece of information that you require. And it lets you create buildings like this, which are phenomenal. Things like the Zaha structures are just mind-blowing. Beautiful structures that previously were not impossible, I would say, but very, very difficult. Okay, so we've come this long way from this manual process, needing to do things very simply, and now through all this digital work, we've come to this place where we can do things a high quality, we can do them very quickly, and we should be able to do a lot of them. But somehow we're still at this point, right? This is our friend Douglas Todd, the Vancouver Sun, saying, why do we only have two tall mass timber buildings in Vancouver, or in BC, I should say? We've gone all that way. Why hasn't it produced? Hasn't it resulted in more buildings? Okay, well, what did they say? We won't pick them apart too much, but let's go into it. Possible obstacles to mass timber high-rise buildings, according to the journalist. Overcoming old fears of fire. Well, we kind of know, right? The science is good now. We've done a lot of the fire testing. I think we've proven this. We have methods of mitigating risk, of fire risk during construction, after construction. So that seems to be fairly settled out. Is timber too light? No, it's actually, well, it is light, and that's a benefit, right? We know there's reduced seismic demand, there's a reduced demand on foundation, so it's actually a benefit in the vast majority of cases. Why go over 12 stories? Well, this is more of a city planning and environmental consideration, right? What is the most carbon efficient? What is the most humane space that we want to live in? So not unique to timber. This is unique, or this is a problem for any kind of building structure. How does the cost of mass timber high-rise compare? I think now we're starting to get to the real questions, right? We've been in all the feasibility studies. We want mass timber for X, Y, and Z reasons. And then it comes to the table, the costing comes to the table, and maybe doesn't pencil out. Lack of innovative spirit. This is the one that hurts, right? This is the one that we don't like to hear. Everyone in the room here prides themselves in the innovative spirit. So, okay, let's make sure that that's not a relevant reason to not be building mass timber buildings, especially here in BC, in this area where we have so much expertise. Okay, so why innovate? Innovation to inspire. Right? You have to inspire something in order for people to want to build it. You have to innovate in order to reduce cost, right? Not everyone wants to build the most unique, fancy building. They also just want to build a building that's economical and that's useful. Okay, so a history of innovation at Fast Epp. What have we been doing over the years to try and get this started, get these buildings going? It's DIY, right? It's men standing on a panel, bending it into shape, right? There's not a single robot in that photo yet. Maybe one day there will be. But it's this manual sort of process, a history of testing things out. Again, I'll put my father hanging from a panel here just to embarrass him one more time. But this sort of DIY sort of spirit has been there all along for us and many of us in the room. Creates a very simple, elegant panel. Long span panels constructed with just simple 2x4s, pine beetle kill 2x4s. In a way that hadn't been done before, right? This is a 3D space truss, just nail laminated together. But again, the testing and the capacity hadn't been well understood of the system as a new system. And so what do? Well, you take some big dumb blocks and you load them up and you see what kind of performance you get from it. A full-scale mock-up of a PSL facade, a multi-story mock-up of a kind of facade system that hadn't been used before. Again, learning by doing, innovating by doing. How much can birch plywood take? It seems a very simple question. It's not in the code. How do we calculate this? Put some weight on it and bend it and try it and feel it and see how it works. The Mannheim Multi-Hull, this gorgeous piece of architecture, of engineering, is falling apart. It's broken. How do we treat that? Well, let's hang some weights from it. Let's see how much more it can take. And let's figure out the pinch points and let's figure out a solution to retrofit it. Test out the materials. See what capacity they have, see where we need to add capacity, see where we can reduce capacity. Return it to its former glory. Glued-in rod testing, this is now becoming a bit more standard. But again, back in the day, this was, these sorts of tests were not, the capacities and the engineering calculations to be able to rely on these structures was not there. And so, again, our friends the cinder blocks come in and you hang something and see how long it takes for that rod to pull out. To do something like Brock Commons, an 18-story tower, the first tower of that kind of scale, a mass timber tower of that kind of scale, relied on not only on that scale, but also a system that hadn't been used much more than sort of small canopies, so a point-supported system, right? So just post-on-panel system. It takes some innovation. How are we going to, at the end of the day, this is a project that needs to pencil out the same as a concrete building, but do it in timber and do it faster and do it in a system that hadn't been done before. So you need some innovation. You need some innovation to inspire, but then to reduce the cost as well. Do a full mock-up and see what it looks like, see if it works. Does this try one connection, try the other connection? Which one is faster? Which one enables you to get that building built to what it was, which is, fairly competitive against concrete and built in a fraction of the time? Put again a bunch of plywood. How does plywood look when it's all assembled together, a mass plywood node, taking forces from a large museum structure? What is that going to look like? How are the forces going to work in there? Do it manually is how we always done it, and working now and towards the digital age, which we'll see right away. These long spaghetti noodles out in Surrey look very bouncy, and they were very bouncy. But how do you know? Well, you go up there and you test them and you jump on them. And as engineers, this is a very, like many of you in the room, it's one thing to see it on a machine, to see it on the model, but what is it going to feel like when you're on it? Is that too much? Is that too little? This sort of tactile, interactive experience is so critical to sort of calibrate your model. The model's right analytically, but is there other factors that we're not considering? And now it's kind of got into much more sort of hardcore testing to push this mass timber into longer spans and more common building applications. Again, doing this innovation in order to, the previous ones were sort of innovation to inspire, to do beautiful structures, and now we're looking at innovation to reduce cost, right? How can we do these timber buildings in an economical way, these common building forms in a more economical way? So put a bunch of screws into these beams and test the long span panels for a gym application in Kitsilano. It's got into the lateral systems, right? Using wood as a lateral element, so in shear walls, shear wall applications here in British Columbia, where we have this high seismic region. What is the capacity of these panels? They have a great strength, but they don't have very good ductility, right? They're going to break, they're brittle. And so how do we develop new connections? Well, work with the universities and do instrumentation and do testing that enables you to do sort of new and novel types of connections to dissipate energy. This is a perforated panel where the yielding happens in those little holes, and so you're tuning those holes in terms of the size and the spacing in order to get just the right amount of slip and energy dissipation at the base. Similar thing here in Alberta. Okay, and just the spans get longer. There's 9-meter spans now. Use concrete where concrete is good, and the compression block up top. And all driving towards this sort of simplicity. So there's inspiration, the innovation for inspiration, now innovation for cost reduction, to make things simpler, easier to construct, right? So everyone in the room has sort of been talking about how do we get it done in a similar cost and quicker and more efficiently. A simple little L bracket with a couple screws hanging onto the beam, and it goes quick, it goes fast, and people are happy. And in the end, you end up with spaces that are inspiring and they're beautiful to live in and beautiful to work in. Okay, so it takes an investment, though. Innovation isn't just free, right? No one's going to, or very few people will pay you to just innovate if there's not sort of an end result there. So it takes an investment. So for Fast Epp, it's been an investment which we've called our concept lab. So we did all that kind of DIY stuff that I showed in the past, just sort of on our own dime and in a yard somewhere in Surrey. But how can we sort of bring that, have a sort of a physical manifestation of that space so that it's brought right into the engineering factory where we work and where we design. So it's in the base of our building, just over in Mount Pleasant, 1 floor, 1.5 floors, I should say, of R&D space. We've got 4 main functions in that space. There's develop, so coming to the table with ideas. How do we get together to make a new connection? What is the driver in why this building is not going to be built? What is the problem we're trying to solve? What's the nut we're trying to crack? Fabricate, let's build it, let's assemble it, let's prototype it, test it, break it, do all those things that I showed before about proving the capacity and working, and how do we do that in a digital way? Right? What is the digital element to all of this that will enable us to do this quicker, faster, and better than we could before? Our development space, just some inspirational trinkets of what's out there and what's been done before. What are the CLT blocks? What do they used to look like? What do they look like now? What are rebar couplers that used to? How can we use a rebar coupler in a wood building, perhaps? And just some space for this is our development hub to just generate ideas. Fabrication with woodworking and metal fabrication, testing frame to allow the engineers to do all the testing required to prove out those capacities that we need to know, and the digital space. Just some little projects that we've been working on. This is just some we have a master carpenter that's been on our in our staff building these gorgeous tables, and seeing that hand in hand with an engineering company it's been quite rare, and it's been quite a nice sort of twist on coming to work. You're used to seeing everyone comes to work and goes to the computer, but now for us anyway, there's many fabricators and other suppliers in the room that are used to this sort of office and workshop environment. But for us, this having these different people with different skill sets, digital, fabrication, robotics, is a very inspiring thing, and it really generates new ideas and shows how craftsmanship can feed into our engineering design to create new buildings. The punching shear testing, we'll be doing a large program of about 200 to 300 panels, breaking those panels in that frame that I showed. And again, this is to enable this point-supported CLT construction typology that is becoming much more common, and which will enable really a lot of multi-unit residential construction to go on, and several of these projects in the book. So a big testing program happening this fall to determine the out-of-plane shear capacity of those panels. Creating digital tools. How do we optimize a truss, which is going to be, which looks about 4 inches wide on paper, but in reality is going to be, 1 story high and about 100 feet long. If you can optimize that thing, excuse me, by even 5% by changing every different element, is that worth it from the fabrication perspective? Putting that into a digital engine and making that optimized for any kind of loading condition, it's things that we work on. 3D printing, again, this isn't the scale of the things that some of the other fabrication we've seen in the room, but this is us just taking our first step at this innovation and this investment in doing things, providing that value add of what do we creatively bring into the table? How can the physical world and the digital world collide in order to do design better, to give us a better understanding how these structures behave? This is a Vancouver Art Gallery project, which will be going up hopefully soon, but a very complex load path, and these trusses that hang off of other trusses that are supported off of different cores, and a very complex system. And so to put it together by hand, to print it, and then to put it together by hand is a very useful and beneficial process, and that allows us to design in a better way. And finally, I couldn't come here without showing one picture of a robot, because that's what I think everyone's doing here. So this is our own little ABB, and this is some of the first cuts after many, many failures and missteps. And we're not in the business of production. We're not in the business of creating widgets and creating many thousands of them, but we're in the business of trying to understand how these digital technologies can enhance our design, can enhance the buildings that we design. And for us right now, it's starting with just simple model making. So little buildings, little arch buildings, and that will be produced on a much larger scale, obviously. But that's our sort of initial foray into this investment that allows us to try and design buildings in a newer way and hopefully a more efficient way. So why invest in all this innovation? What's the point? To create spaces like this, to create spaces like this, and to create buildings like this, most importantly, which is housing for people. That's it.